Hola, ¿cómo estás? Bien? Sí, ¿dónde estás? ¿En México? No, Wisconsin. So that was my Spanish. Learned Spanish once upon a time in high school, but that was my effort at Spanish. The reason being is the picture I chose behind here was actually from a resort that I went to in Mexico. Um, I don't remember. In 2014 or 15. One time I've ever been to Mexico. It was pretty awesome. So, but I didn't learn a lot of Spanish there. But anyway, this is section 10.8, which has nothing to do with Mexico, but it does have to do with geometric probability. So here's the goal for you, or the objective. It says to use segment and area models to find probabilities of events. So we're connecting probability with what we've been talking about in with geometry. So let's start off with what geometric probability is in its most general form. So this means the probability of an event occurring. So the probability of an event occurring would be equal to the number of favorable outcomes, and those are what you're looking for, over the number of possible outcomes, which would be the total possible. Which just is really like um, what you'd probably think of when you think of probability. Like if you're flipping a coin, and you want heads, that's the one outcome, and there's two possible outcomes. Your probability would be 1 out of 2. Same thing goes with geometric probability. So let's look at problem 1. It says using segments to find probability. It says point K on line ST is chosen at random. What is the probability that K lies on QR? So if we look at it, ST goes from 2 to 14. So 14 minus 2 would be 12. So we have a total of 12, right? Because we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 slots there. 12 lengths there. And if we're trying to find the probability that's in QR, so the favorable outcomes would be we have 1, 2, 3 of them total. So 3 favorable out of 12 would be 1/4. That would be your probability. All right? Make sure you're looking at the correct favorable outcomes and the totals. Don't assume that you have a total of 14 when it just starts at 2. All right, problem 2. Another one that has to do with probability here. It says a commuter train runs every 25 minutes. If a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait at least 10 minutes for the train? Use segment probability. So I'm going to use this hour. We're going to say this is our hour, 0 to 60 minutes. And let's say it comes every 25 minutes. So let's say the train runs every 25 minutes. If a commuter arrives, so let's say at 25 minutes it runs. So this would be 30. Go 5, 10, 15, 20, 25, 30, 35, 40, 45. Whoa. 50, 55, 60. All right. So I'm just going to mark when it comes. So 25 minutes would be right here. The other 25 minutes would be right here. That's really all we have to look at. So the parts that would be waiting at least 10 minutes for the train. Well, let's say you got on right here. This would be 10 minutes. So 10 minutes would be here. But like 25 minutes ago, this would have been another one. So anywhere from here to here, you'd have to wait at least 10 minutes. Because if it was here, well, actually, it'd be anywhere from here to here. Because once it leaves, then you have to wait more than 10 minutes until here. Same thing would be here. Then you have to wait more than 10 minutes right here. So really, you just have to look at one 25-minute span, and 15 of those 25 minutes are favorable for waiting 10 or more minutes of 25. Um, so 10 or more minutes. So that would be anything more than 15 would be, then you'd be waiting less than 10 minutes. So it'd be 15 out of 25 every time. So 15 out of 25, 15 out of 25. Same thing. And that can reduce then to 3/5, I believe. All right? That was a little bit more tricky one. You just got to draw it out and kind of picture, visualize what's going on here. All right, still looking for favorable out of total outcomes. Now, the second thing that we're going to deal with is probability and area, since we've been dealing with some things with area. So point S in region R, so this is our whole region, the picture to the right, is chosen at random. So we're choosing a point at random. The probability that S is in region N is the ratio of the area of that region to the area of the total. So this would be your favorable. That doesn't really look like favorable. And that would be your total. Still the same idea. We're just dealing with an actual area now. So let's see how that looks. In problem 1, it says a circle is inscribed in a square. Point Q is in the square is chosen at random. We're going to choose a point at random. What is the probability that Q lies in the shaded region? So the shaded region would just be on the outside. Round your answers to the nearest tenth. So let's look at the total area. Total area would be 6, it's a square, so 6 by 6, which is 36. So the area of the square is 36 units squared, or centimeters squared. We're at 36 on the bottom there. Now, if you are going to find the area of the circle, that's great, because that's the other part that we could find. We can't really find the area of the shaded parts just by using a formula, but the area of the circle would be, if this is 6, the area of the circle is pi r squared. So the radius would be 3. So 3 squared is 9, so it would be 9 pi. So 9 pi. So, but that's not what we're looking for. We're not looking for the area in the circle. We want to subtract 36, or that from 36. So essentially that would be our, so the area of the shaded, let me just draw that here, then the area of the shaded would equal the area of the whole thing minus the area of the circle, which is 9 pi. And that's where we put that over 36. You can leave it at that for right now. It says round your answers to the nearest tenth, so we're going to actually take a calculator and figure out what that is. So I'm going to do that. I'm going to pause right here and do that. You can do that on your own as well. So when I do that, I get 7.7-ish over 36, which would be 0.2 overall. So 20% of it actually is shaded. So that doesn't maybe look like 20%, but 20% of it would be shaded. Unless I made a mistake, which you could find and show me next time, but I don't think I did. All right, going on. We've got 2 problems. I'd like you to try these on your own first. If you want to pause these and try these on your own, but I will go through them as well. So I'll go through the first one right now. In the fundraiser game at the right, players toss darts at a board and try to get them into one of the 5 holes. So you've played games like this probably, where you just toss bags into the like a beanbag toss sort of thing. The diameter of the center hole is 8 centimeters, so the whole thing is 8. And the diameter of each of the 4 corner holes is 5. These are all 5, the diameter. And the board is 20 by 30. Find the probability that a toss dart will go through any of the holes. So basically, we want to find the probability of scoring. Would be the probability of, or the area of the holes. Those are what we're going to get into. That's our favorable one over the total area. So the area of the rectangle. So the area of the rectangle, I think we can get pretty easily. We'll make that 30 times 20, which is 600. We're not going to use units right now because we're just doing probability. And let's find the area of all the holes. So we have, area would be pi r squared. So we have 14, or 4 squared would be 16 pi. And each of those would be half of, so it would be 2.5 times 2.5. 2.5 squared. You get 6.25. So those would be each be 6.25 pi. So add those all up, because these will all be 6.25. Add those all up, we get times 4 we'll do, plus 16. We get 41 pi. we're going to find that. We're going to use the calculator to find that now. So I got the 41 pi would be about 128.8 over 600 would get me 0.21. Very similar to the last one, but 21% of the time we get it in a hole, assuming that the entire thing has the same amount of chances of landing on or in. All right. Now one more, dealing with shooting arrows, so archery. An archery target has 5 colored scoring zones formed by concentric circles. The target's diameter is 122 centimeters. The whole thing would be 122 centimeters. The radius of the yellow zone is 12.2. That's the radius. So the radius of the yellow zone is 12.2. The width of each of the other zones is also 12.2. So each of those widths is 12.2. If an arrow hits the target at a random point, what is the probability that it hits the red zone? So looking at that, why don't you try to do that on your own? But this would also be 12.2 then. I'll bring that over here. 12.2. All right, so before we go too far on here, the way you find the area of just the red, just remember the total would be the total whole target, the area of the whole target. But the area of just the red, you'd have to take the area of this circle that makes up the red and the yellow, and then subtract the yellow part because we don't want it to land in the yellow part. We just want the red part. So that's what I'm going to do to find my probability here. All right, keep going. So checking out all the work that I just did, I found the area total for the just the red part would be 1,372.2 centimeters squared, and then divided by the total area of the whole thing, which was 11,689.9, and that got me a probability of 0.12, or 12% of the time I land in just the red section. So again, that's probability, that's geometric probability, using the areas that we've learned and finding the probability that you can land in the red section of this target. We'll look at this next time, problem 6, see if you can figure it out a little bit. Go for it. It has to do with volume of a sphere. And then please do answer the 2 closing questions. What is theoretical probability? How is that calculated? How can a geometric model represent probability? So we didn't use the word theoretic probability, but that's the same thing as our way of finding the geometric probability. It's all in theory right now. We're not actually testing it. But how can a geometric model represent probability? All right. So then go back to our goal and see what you learned, and we'll see you next time. Have a good one.